Our next speaker is Maciej, and he's going to talk about hunting bugs. And how do we hunt bugs? We do that by sending a bunch of random input into our programs, or more scientifically called fuzzing. Round of applause.
All right, welcome. So in the spirit of testing, let's talk about fuzzing. So I'm Maciej. I'm an offensive security engineer. I've been previously a platform engineer and software engineer. I sail, climb, and play board games. So what we'll talk about? We'll talk about fuzzing. We'll talk about differential fuzzing, how it differs from fuzzing. And we'll talk about bugs that are in the standard library and how you can actually find those bugs and fix them using fuzzing. And then at the end, we'll talk about fuzzing in continuous integration pipelines. So, what we'll not talk about is how fuzzing works under the hood. There are excellent resources out there that will talk about like fuzzing engines and like other stuff. I'll link to them in the end, but this talk is not about this. Why should you care? So, there's an OSS Fuzz project. Who is familiar with this? Cool. So, this is a kind of a platform that gives open source projects compute resources to run fuzz tests continuously. And there's about 1,000 projects in there, and within 6 or 7 years, it has found 10,000 vulnerabilities and 36,000 bugs. And if you do a simple maths, that's 10 vulnerabilities per project and 36 bugs per project. So, this seems like an effort that's worth investing in. So let's assume we have a simple function. It accepts the string, mutates it, and gives you a transformed string back. And it transforms, letters or characters in the alphabet to a character that is 13 positions later. You get N for A, O for B, and P for C, and so on and so forth. So in your regular testing, you'll come up with some inputs. You put those inputs into the function, and then you'll make assertions based, if the output is correct. You're all familiar with this. Probably you can run this using your, standard Go CLI. With fuzzing, the situation changes a little bit. Instead of your, device input, your things you came up with, you have a random input. You put it into function and make some assertions. It looks very similar and is supported in Go from like Go 1.18, and you can also run this using the CLI. You see some boilerplate around the test, but in the middle you basically have your unit test that you had before. I intentionally left the assertion blank because how do you assert and stuff if you don't know the input, right? If you run the fuzz test, you'll see that it tries hundreds of thousands of inputs per second in this instance, and it runs indefinitely. So you can run it as long as you want. As we've seen, it's easy to create fuzz tests if you have unit tests in place. So there is no reason not to do it, really. One thing that we haven't talked about is that it's not all magic. You still have to kind of instruct the fuzzing engine to be able to come up with inputs that make sense for your test. So you can actually reuse the inputs you use for unit tests and add them to what's called the corpus, and that tells the fuzzing engine to come up with something that's similar, but quite random as well. Yeah, add the inputs from your unit test. That helps a lot. I've talked about those assertions that it might be pretty tricky to come up with them if you don't really know what the input is. So what you commonly see in fuzz tests is that they don't make any assertions. They just the engine just checks if the function crashed, which is still very efficient because it tells you that there are some out-of-bounds size accesses, for instance. But you should and can assert on invariants, those things that don't change. And in our instance, for instance, there is a property to the rot13 function that you can actually call it twice, and you'll get the input back. And this holds true for anything that has an inversible. So, if you have an inverse function, you can make a simple assertion like this, which is just call rot13 and rot13, and then you expect the input back. And if it doesn't agree, it's the test fails. Some examples that are in the commonly used are encoders, decoders, marshallers, and marshallers. You can just call the things, decode the encoded thing, and you should get the input back. There are other stuff, like if you do a SHA sum, for instance, you always expect it to return 32 bytes. But there is other technique. And what if you had two implementations of ROT 13, right? Something that you wrote and then something else. And that's called differential fuzzing. So basically, you get a random input, you put it through two implementations, and you see if they disagree. So think about for a moment, and where can we get those second implementation from? The first thing is refactoring. Let's say you have your function, but I don't know, it's unreadable, maybe it's not performance enough, so you're refactoring the code for whatever reason. You can save your old implementation to the side and use it to basically reference it when you refactor the code. The second example is performance. You might maintain two implementations in the first place. For instance, you are following a specification closely, and the first implementation is written very close to the spec, but it might be inefficient. But the second one is heavily optimized, but it might be not quite readable. You might have some shared buffers or whatever. The third option, which is really interesting, is that there is a C library that does a similar thing. And you can use Cgo to call it, and that's what we'll explore further. So back in January last year, I saw an interesting bug report, and I think Go Weekly newsletter, where there was an issue with the HTML tokenizer, basically a piece of or part of the experimental library that does HTML tokenization. And the thing was that it was incorrectly interpreting comments, and this led to an XSS attack. So what does an HTML tokenizer do? It basically takes a HTML input, and it gives you the HTML token. So for this example, for instance, you have a paragraph and a text inside, and an anchor afterwards. You'll get start tag of P, text, and then the text inside, end tag of P, and then start tag of A. This is a very well-defined process, and there is an HTML specification for it. It's very high in detail, it's easy to follow, and it's a state machine, which will become important later. If you look at the Go implementation, though, it's not a state machine. And it's not quite easy to follow, at least for me. So I thought, if there was a report for it, then there might be other bugs lurking around. So let's use that function a bit and make another one that gives you a list of tokens, because the API works in a streaming way. So we'll just call the tokenizer, collect all tokens, and then return the tokens it generates. So when we, let's say, start with the fuzzing, we will supply some HTML inputs to the corpus, and then call the tokenize function without making any assertions. And there are no results. It doesn't crash. And that's something what we expect from some library or from the experimental part of it. So let's try differential fuzzing, right? We'll have our tokenizer function that we wrote and some alternative implementation for it. And if they don't agree, we'll fail. And as you can imagine, because the C ecosystem is very mature, there probably is a library that does the same thing. So in this case, I found Lexbor, which is a web browser engine that is a software library. It has no extra dependencies, has Apache 2.0 license, sounds about perfect for what we want to achieve. So don't look at this slide, really. It's basically implementing the tokenize function that we implemented using the Nets HTML tokenizer, but using the Lexbor. It's actually a lot more complicated than that, but will be good for our tests. So we call the tokenize and Lexbor tokenize and do some equality checks, and if they fail, we fail the test. And it found something. So there is some weird-looking HTML code, looks malformed, and Lexbor says that it's an A tag, but Net HTML library is like, oh, there's nothing in there. So let's transform this a bit, and let's see what the browser thinks. So we have a disagreement. Could this be a security issue? So what if we made trust decisions based on the tokenizer? And so imagine you have like some user input on your website, you accept HTML input, and you decide whether the stuff people input is safe to display or not. And you should, by the way, you really shouldn't do this, but we'll have a isSafe function that will return a Boolean, whether it's safe or not, and we'll just look for the tokens we get and only allow strong tags and nothing else. Strong tags and text tokens. So the isSafe method thinks that the thing that we got from defuzzing is safe because it thinks there's nothing in it. But the browser says otherwise. When you look at the documentation, though, there will be a security consideration section in the HTML tokenizer. And it says, care should be taken, especially with regard to untrusted inputs. If your use case requires a well-formed HTML, the parser should be used rather than the tokenizer. So let's implement this using the parser, right? I want to go into detail, but we use the parser here. That's also in the same library. The thing is, the parser also thinks this is safe. And the reason is it uses the tokenizer underneath. So it doesn't really differentiate between the two. So we still get the XSS. So we have two things. The first thing is that the documentation could be improved because it's unclear. It steers you in the wrong direction. And second, that there is a bug in the tokenizer. So I thought, right, if there was a vulnerability report in the VRP program for the comment thing, I'll do the same thing. So I submitted a VRP report. There was some back and forth. They closed my ticket. I told them to reopen it. They reopened it. Whatever. And the result of that was that there was a documentation update, which is cool. And they say that in security context, if trust decisions are being made, the input must be reserialized, for instance, using render or token string. So what they are saying is that instead of doing isSafe function that returns a Boolean, you should actually transform the input and construct it in a way that you basically sanitize this, transform the string. And there are two ways to do this. One is to use the token.string function, which when you loop over the tokens, you can reconstruct the inputs, or render when you use the parser. A few months pass, and there is a commit to the library. And they fix the actual bug. So, handle equals signs before attribute, and they quote the spec and fix the bug that was there. So now if you call the isSafe function, it returns false. That's pretty cool. But let's run the fuzzer again. I mean, you get something that is very similar, and it acts the same way. So I thought, all right, I have this fuzzer. It's not pretty. It has no way to reach the standard test suite, but we can, learn the code base and iterate over it. Run fix the problem, run the fuzz test again, and then, So I prepared the patch, and you've seen Garrett's screenshot today already. It passed the code review, but as Jonathan mentioned, you need a lot of patience. It's been stuck in ready to submit for 3 months, I think. So it still hasn't reached master, but it's close, I think. But when you run the fuzz test again, there are no more findings. So the takeaway from this is that fuzzing is very effective, and differential fuzzing helps write correct code. So let's talk about what are good testing candidates. We've used it on parsers, which are pretty complex codes. You can use them on decoders, encoders, marshallers, and any complex code that can be unit tested, basically. But running those tests in CI is kind of problematic, at least in my experience, because it's not really mature enough yet, I think. And when you run the go test fuzz invocation, it can only run a single fuzz test. So people have been doing a lot of hacks, like grabbing the source code, trying to find those fuzz targets, sleeping, some pretty hacky bash scripts, for instance. There is also a very cool project called Cluster Fuzz Lite. It's actually a subset of OSS fuzz that you can run in your CI, but we found some problems with it. First, it has problems with extracting failing inputs. Like if you have a byte array, for instance, it it doesn't really translate one-to-one to what the actual input is, because you have to apply your own transformations over it, and it's pretty inconvenient to run locally. So we built Go CI Fuzz, and it's kind of a lightweight wrapper around Go Test Fuzz. And it supports multiple test targets, and it allows you to extract inputs. So if you want to give it a try, there is a link here, and yeah, give it a go. It's basically plug and play, drag and drop. You can use it to run fast tests as part of your pull request workflow, or you run it on schedule, so like during the night or whenever you want to run this. All right, so we've blazed through it, but yeah, if you want to say hello, there is my email address and my handle, and also I wrote a blog post about this that goes more into detail about this actual finding, and there are some references. If you want to start fuzzing, there is a very excellent introduction to it in the Go documentation. There's also good article on Wikipedia on how it works under the hood, and there's a link to Cluster Fuzz Lite, the Go CI Fuzz, the blog post, and also a pretty interesting entry in this list is the second one. So there was a recent paper from Google where they use AI to actually generate the fuzz tests. So maybe you don't really need to write them, and AI will be able to do it for you. All right, so if there are any questions, happy to answer. All right.
Are there questions? We still have some time.
One.
In the front, that's nice.
I can yell.
Okay.
So,
Yeah, the video can.
How many minutes? Okay. How many minutes do you run the fuzzer in the CI? Because this is important, right? Because it costs money.
That's true. Yeah. So it depends on the workflow. So for instance, when it's a pull request, you really don't want people waiting. We run this for like 5 to 6 minutes. It's enough time in our experience to catch like those bugs that are, the edge cases that are quite common. But you can run this indefinitely during the night, and it depends on how much money you want to spend for your CI runs. Yeah. All right, any other questions?
Questions? Can you keep your hand up and I can go to the right row? If you could pass this along.
Have you tried to fuzz only inserting random strings, or like also combination of valid tokens in different order?
Could you repeat, sorry?
From what I got from the slide, if I'm not wrong, you were like inputting random strings, right?
Okay, so how it works really is that you provided a starting corpus. So like think about your unit test inputs, and then the fuzzing engine underneath takes those inputs and puts transformations on them, right? So every time you'll get a slightly different input. It won't be completely different, but it will be a bit malformed. So like if you saw these, the findings, for instance, here, right? It outputs a valid HTML or almost valid HTML. So it kind of reached this conclusion based on some coverage data it found. So like it also looks at test coverage. So when it runs the fuzz test, it kind of captures which branches of code have been covered and tries to reach the other that have been not covered. So it's kind of an iterative process where it applies transformations to the inputs. Right, there's another one.
How does the engine know which part of the corpus it may change and which not, so it doesn't only input like random strings as I could obtain from the random package?
Could you repeat the beginning of the question?
Yeah, sure. The fuzzing engine, you give it a set of example strings.
Yeah.
How does it know which part of that it may change, and so that it doesn't just put in random things?
Okay, so I don't know the exact details, but I think it works that it makes a change and it looks at the coverage data, right? So it looks at the branches. It kind of discovered when it made the change. And it will note some interesting inputs and then try those inputs. So like if the coverage increases, it will, try to make more transformations similar to the one it makes. Yes, one more.
What kind of coverage metric is it?
The question is what kind of coverage metric it is. I think it's, I'm not so 100% sure, but I think it's branch coverage based. If you run the fast test with some variables flags, you will see that there are coverage bits, and I think it tells you how much coverage there is for a particular input. All right, there's one more.
1 second.
I can probably just
Yeah.
speak loudly. Running fuzzing is costly, and you already talked about like how do you pick the time period that you run it for. In Go, there's a very handy Go cache since a couple of releases. Is that something you could bring into your fuzzing tool as well? That you say something like, oh, you already run the fuzzing test for an hour, let's not do this until the code actually changes?
Yeah, so the question is, there is a Go cache, or when you run fast test, there is a cache folder that it will capture the inputs it already run, and the question is whether the tool will or can support this. And the question is the answer is it doesn't right now, but it's planned. So for those that are unaware, when you run run fast tests, there is a directory that will capture all the input it has tried, or the interesting ones. And when you run this again, it will start from that point, which is really handy because you will not do the same work every time or similar work. You can start from where you left. Yeah.
Thank you.
Yeah, there is one more.
The question is slightly tangential to this directly, but you said we provide a starting corpus, and then there's transformations on that, which is run against whatever we're testing. So is there a way to optimize the starting corpus to increase the kind of test cases that are actually generated by the fuzzer? Or is there a way where the starting corpus can be designed to cover as many edge cases as possible?
Okay, so there are similar kind of perspectives to this. There are corpuses that you can find online in GitHub, for instance, that you can employ in your fast tests. Also, when there's a finding, for instance, so when you run the fast test and you find a string, it will add it to the corpus that you have in your repo. So when you run this, there will be a directory created in your repository that's called test data, and inside that test data folder, this input will be captured. And you should actually commit that folder to your repo so that every next time you run the fast test, it will actually check for regressions. So yeah, I hope this answers your question. Yeah, any more?
Thank you. Are there ways to customize the kind of transformations that are applied by the fuzzer?
Not in the Go native. Not in the Go native fast test. So there are other tools that have been used before, and Go introduced native fuzzing. There is libfuzzer, for instance, that's very commonly used by the OSS fuzz. And I believe if you use that, you can customize it. But the way native Go tests work is that they actually use the libfuzzer, but it's not very configurable. So it's supposed to be good developer experience-wise and cover most of the needs you need, but I don't think you can drive the transformations from it.
I'm going to end the questions here. Last applause, please. Now, before you go,